Welcome back. So in this slideshow, we're going to just walk through a bunch of practice problems and I'll give you a chance to respond on your own before I attempt to explain the responses. So let's go ahead and get started. First question, what percentage of daughter isotopes exists after one half-life? If you said 50%, congratulations, you're on the right track. A half-life is defined as the time that it takes for 50% of the parent isotopes to decay into daughter isotopes. All right, next question. What percentage of parent isotope is left after two half-lives? You said 25%, great job. So after one half-life, you'd have 50% parent, and after another half-life, you'll only have half of that. So after two half-lives, you would be down to 25% parent. On the other side of that, you'd be up to 75% daughter. If a sample is 12.5% parent, how many half-lives have occurred? Take a second. Hopefully you said 3. One half-life, 50%, two half-lives, 25%, three half-lives, 12.5%. All right, if radioactive decay began with 400,000 parent isotopes, how many would be left after 3 half-lives? If you selected 50,000, great job. So after the first half-life, you'd have 200,000. Second half-life, 100,000. Third half-life, 50,000. The half-life of a radioactive isotope is 500 million years. Scientists testing the rock sample discovered that the sample contains 3 times as many daughter atoms as parent atoms. What is the age of the rock? All right, so if you selected 1,000 million years, awesome job. Now, this one's a little bit more complicated, so let's talk about it in some more depth. All right, we know that the half-life is 500 million years. Okay, so I'm just gonna underline that. And we also know that the sample contains 3 times as many daughter atoms as parent atoms. Well, that's the same thing as saying that it is 75% daughter. Well, if the sample is 75% daughter, that means it must be 25% parent. Now, we just need to figure out how many half-lives have passed. So, if we go ahead and draw ourselves a nice little decay curve to help us out. We know at time 0 it's 100% parent, after one half-life 50, after two half-lives 25, and so on. So we can draw on our curve. Now, 75% parent means 75% daughter means 25% parent. Okay, so it looks like that happens after 2 half-lives. So, given this is the half-life, 500 million times 2 equals 1,000 million years. Okay, good job. Next question, radioactive isotopes in clastic sedimentary rock always predict an age that is older, younger, or correct for the sedimentary rock. Take a second to think about this one. You said older. Great job. A classic sedimentary rock is always comprised of the pieces of pre-existing rocks. By pieces, what do I mean? I mean the mineral grains, right? So these little time clocks, they start when the mineral is first formed, not when the rock is first formed. So minerals can go through the rock cycle and be in multiple different rocks, right? Maybe an igneous rock and then a sedimentary rock. It's always going to tell the time from when the mineral was first formed, which in the case of an igneous rock is also going to be the age of the rock. But in the case of a classic sedimentary rock, it would be the time when whatever came before formed. So you can't use this method on a classic sedimentary rock. All right, what percentage of daughter isotopes exist after 4 half-lives? Hopefully you're starting to get this. Now for me personally, I find it just easier to think about the parent. So if I step through 4 half-lives of parent, that would be 50%, 25%, 12.5%, and then what, 6.25 or so, okay? Now, the daughter is going to be doing the opposite thing there, right? So if I take 100% minus that 6.25, it will arrive at this 93.75% daughter, okay? So you can do whichever is easiest for you, but personally I like to sort of decrease from the parent. Half-life of a parent isotope is 50 years. 75% of the sample has decayed into daughter. How old is the sample? All right, kind of already done this one. So cross your fingers. Hopefully you get it right this time. Did you recognize that the sample is 100 years? This is just like a problem we already did. So this says 75% equals daughter. That means 25% is parent. Okay. And we get to that level after 2 half-lives, right? So 1 half-life, 50% parent, 2 half-lives, 25% parent. So we're talking about 2 half-lives. And then we take the value of the half-life, that's 50 years. We multiply that by the number of half-lives that have passed, which is 2. 50 times 2 gets us 100 years. Okay. Half-life of the parent isotope is 150 million years. What percentage of parent atoms will remain in a sample that is 300 million years old? Did you say 25%? So the key here, as with pretty much all of these problems, is to figure out how many half-lives have passed, okay? So if the half-life is 150 million, and we want to know how many will remain after 300 million years, well, 300 million would be 2 times the half-life, 2 times the half-life, okay? And we know that after 1 half-life, you're at 50% parent, and after 2 half-lives, you are at 25% parent. So I know it's a little bit confusing at first, but hopefully this is starting to get a little bit repetitive. You're always figuring out how many half-lives have elapsed and then relating that either to a percentage parent or an age. Okay, great job. I hope this helped, and just keep studying.